We were interrupted there trying to create a CD and apparently using more system resources than usual. I don't know what the problem was. In any case, we see the CD and its reflection. Now if we turn the CD this way, of course, its reflection, not its reflection, but its shadow, pretty much disappears. So I'm just going to hold the CD a little bit lower, and we can see what happens as we rotate. Now right now, the flux is being intercepted by the CD. The flux on the surface of the CD, the flux that's trying to get through the CD, is a maximum. If we rotate it this way, the flux becomes a minimum. Now if we continue rotating, the normal vector's in the opposite direction, so the flux is actually on the opposite side of the CD, and we're going to say that's a negative flux, so we have a maximum magnitude of the negative flux, and then we rotate some more. We get back to zero flux, and then back to the positive flux on the front of the CD. Okay? And we can see how the normal vector is represented by my finger, if I can get it into the light. Okay, normal vector is pointing right at the source here. If we rotate 180 degrees, it'll be pointing away from the source. Positive and negative depend on our convention for the positive and negative directions of the field, and also depends simply on the arbitrary choice of which direction around the loop is positive. I just arbitrarily chose the front excuse me, of the CD to be a positive orientation of the normal vector, the back to be a negative orientation. Now, the flux is represented by phi, and it turns out that that's just the field times the area, which is what we get when we intercept the maximum flux. Again, when we have the CD here, we're intercepting the maximum flux. When we have it to a side, we're intercepting zero. There it's a negative flux, zero, positive. As the angle of the normal vector, which is represented by the marker here, changes, we intercept less and less of the area. You see, when we're at a 45-degree angle, we don't intercept as much. When we're at a 90-degree angle to the light, to the direction of the light rays, we intercept a minimum. We get that by multiplying the field times the area, then by the cosine of theta. So that the flux is B times A, magnetic field B times area A times the cosine of theta. At the 180-degree orientation, that flux would be negative B times A, because the cosine of 180 degrees, of course, is negative 1. And that corresponds to this picture where the normal vector is opposite to the field. Now, when the field and the normal vector are in the same direction, the angle is 0 degrees, and the flux is just B times A cosine of 0 degrees, which is B times A. Now, what has happened? Between here and here, the flux has changed from negative B times A to B times A. That's a change of what? That's a change of 2BA. So that our flux change is 2BA. Now, the average voltage that we get out of a flux change depends on how quickly the change takes place. If I change this orientation very quickly, from here to here, very quickly, then the change takes place in a short time interval. And the average voltage is higher if it happens quicker. You saw that with the galvanometer. If we move the magnet slowly, we don't get much voltage. If we move it quickly, we get a lot of voltage. So that our change is, our average voltage is going to be the average rate at which the flux changes, delta phi over delta t. In this case, that's 2BA over delta t. I'm rushing to stop this because I'm afraid we're going to get stuck again. So we'll go on with this in a second.